In this presentation today, I'm going to talk about the application of geochemistry in mineral exploration. Basically, what I'm going to do here is to highlight, the exploration within Queensland itself, and to talk about the different data sets, that's available to help industry. In this talk, I'm going to talk about the background of exploration geochemistry, basically about the transformation of chemistry, from what it was until what it's going to be. Then I'll sort of delve into the core of this talk to sort of discuss the different criteria for successful and cost-effective, expression. Basically, understanding the geological setting so that we could find the right samples, the right techniques, which is basically what the geochemical toolkit is, and then highlight the different data types that's available in Queensland and the importance of utilizing, all the different data, including the measures and the trace elements, to get a good geological understanding to be effective in this geochemical exploration. Also, it's really important to take advantage of all the archival data and the free knowledge-based information that GSQ has produced, as well as the collaboration that we have done with other organizations, so that this could be used by industry to sort of expedite, as well as to expand their sort of exploration targeting. And it's really important, I think, we have come to a phase where most discoverable deposit has been found, and then we have to adopt new technologies like high precision multi-element geochemistry, hyperspectral, continuous XRF scanning, etc., to help with the future discovery. And finally, I'll discuss about the leverage with research organization and other geoscientific uh, programs, to enable this sort of work to progress, at a minimum risk or exploration risk to the company itself. The first pictures, shows here, shows the mineral discovery in Queensland. Basically, Queensland has been a very active exploration target, for the last 150 years. Before the Second World War, within this first 80 years or so, a lot of this discovery were done just based on good science, good geology, and good knowledge base, which we brought in miners from overseas as well as from other parts of the world to find the gold and tin deposits, in both Palmer River and in the Darling Downs. It's only after the Second World War, the geochemistry, geophysics, and geological modeling were used in the discovery of mineral deposits. And in the 80s, where computer becomes fashionable, things like GIS, modeling, and other sort of computer-related science were adopted. Nonetheless, if you look at the trend of discovery, it starts to sort of fall off, and we were sort of held back, by good science, until about 1980s, and after that it starts to taper. And one of these reasons is that a lot of this easily discoverable deposit has been found, and then we are forced, or we have to face the highly um, difficult to find, deposits undercover itself. Well, the background of geochemistry, or the success of geochemistry depends really very much on good science, that's good knowledge base, and as well as good data. And both science and data evolve through time. And that's a really important sort of concept, I think, for explorer to understand. In terms of geochemical exploration, the philosophy has changed tremendously in the last 50 years. In the early part of these 50 years, most geochemistry are there to actually identify or to analyze material, which one needs to know what the content is to decide whether it's an ore material or it's not, and then to look at the expansion of those non-ore materials outwards to basically define, where the margins of this ore deposit is. Whereas later on, geochemistry, exploration geochemistry has moved into detection work, where it has, used very highly sophisticated multi-element chemistry as a tool to try and sort of discover the pathway of chemistry, where to where site is. In other words, it's used as a tool to try and sort of decide or discover where the source region is. So that's the big sort of shift from determinative, sort of chemistry to detective chemistry. With this revolution, there is a lot of emergence of new exploration science. And basically it talks about, new samples, new sampling techniques, preparation, digestion, extraction techniques that's, new, and also very sophisticated instrument that enables, the industry to find very high precision analysis itself. Well, with all these advances in chemistry, exploration becomes very expensive, and it's generally in today's, sort of exploration, it's balancing between cost factors and how effective it is. And that's why I will talk about collaboration, and archival data sets, in the later part of this talk, where you could cut down some of this cost by using ideas and, sort of finding that has been, you know made by scientific organizations. This is how the chemistry has evolved over time. It is an evolving chemistry. As I mentioned, in the earlier part of the century, most of these geochemistry is within this realm, where this is the concept is, when you have a grain, a mineral grain, and it has a sort of thin coating of transient mineral, or mineralization on top, or just mineral on top of it. You, in the earlier years, a lot of these are conventional chemistry, because a lot of these mineral grains are derived from ore material itself. So to determine, how good that ore material is, you try and dissolve all of them as complete as possible. And so it come up with this multitude numbers of, acids, from the highly corrosive, hydrofluoric acid that digests everything, to the four acids, to the aqua regia, and to the different acids, pure acids of different concentration. The idea is to get as close as possible a chemistry that reflects the ozone or the material that you collect, so that you know whether it's ore or it's not. However, with the change in the philosophy, where a lot of these deposits are undercover, a lot of this chemistry, the transient chemistry, goes to substrates or just cover sequences that has nothing to do with the mineralization. And a lot of this chemistry are just sediments, substrate, that you don't want the chemistry. For example, if you were to dissolve everything, you get a very strong dilution factor from that chemistry, from that mineral grain. What you are interested is just that little veneer of chemistry on the grain itself. And so it came out with a whole series of partial digestions. It goes for the more aggressive ones that digest, more into the grain, to ones that just edge or just displace those, exchange cation, within the material itself. And so this is where this big shift in exploration geochemistry is. And I think, explorer has to recognize that big shift from a determinative chemistry into a detective style chemistry, to try and sort of discover where the new deposit is. Therefore, the geochemistry exploration has evolved tremendously, with a lot of new thinking, a lot of new technology, and therefore it requires a lot of new equipment or instrumentation to achieve that. Now, what's the sort of requirement for a successful geochemical exploration program? Basically, I'll go into the 5 points that I mentioned earlier. The first of the criteria is to be able to understand the geochemical setting. Basically, in geochemical exploration, there are only two settings: the outcropping and the undercover setting. Both of them had very similar geochemical sort of, expression, except one of them is undercover. The difference of them is this. I'll just go through them briefly. A first scenario in the exposed area is that the actual ore material gets exposed to the surface. And therefore, when you pick a surface in a sample, just analyzing it, just dissolving the whole thing, you will have a good idea what's the grade of, of that ore material is. The second sort of, scenario is when the material gets to the surface and it gets broken down into daughter products like gaussons, laterite, etc. And by analyzing those daughter products, you still have a link back to where the original deposit is. as well as the chemical signature is. The third concept is that you had the deposit that's deep inside, but there is a conduit to link the ore deposit to the surface where the sample is taken um, by things like fault or a vent or something where the fluids or the material can come to the surface, and you could sample that surface, giving some indication of what the material is at depth. And like both scenario, you had this last sort of scenario where you had deposits that is deep seated within, it's hidden, that has no signatures to the surface. And these are ones that are the biggest challenge, and I believe there's a lot of this in the Mount Isa inlier, where you need new techniques, salt gas, hydrogeochemistry, etc., to find this. On the other hand, in the cover sequence itself, you have the same scenario, except you had this sedimentary cover that has nothing to do with the ore deposit itself, that acts as a barrier for the chemistry to get right to the surface. In shallow deposits, the chemistry could still, sort of migrate or diffuse to the surface, and conventional geochemistry might still work, or it forms like a gossamerous secondary deposit at the unconformable layer, expanding this footprint, the geochemical footprint. And if it's shallow enough, you could still pick up the signatures. However, in a lot of cases, when the sediments gets thicker, this kind of simple scenario does not exist, and a lot of this chemistry are hidden from the surface. Although there are a lot of things like the formation or dispersion of this chemistry along unconformable layer is what explorers are looking for, because it expands the footprint of that chemistry. However, if you got thick cover, it would not come to the surface, and therefore you depend on transfer medium like plants or biochemistry or groundwater to be able to sort of transfer this chemistry right to the surface itself. And then you had those hidden deposits. It may be exposed at the unconformity, but it doesn't get to the surface, and therefore things like porous, if it's porous enough, salt gas, etc., applies. However, in all the scenario for these hidden ones, drilling is still the sort of answer to the discovery of hidden deposits. So basically, in exploration chemistry, it's really important to know what geological setting you are in, so that you could choose the right geochemical techniques that's suitable for detecting, buried or undercovered ore deposit itself. And what's needed, especially in those deep-seated deposits and undercover deposits, it's high precision, high sensitivity, and sample that's dense enough, so that the signature, this very weak signatures, could still be picked up at surface itself. This leads us to what the geochemical toolkit is. Basically, the geochemical toolkit summarizes what I've spoken about, in the previous few slides. In the geochemical toolkit, it's basically an exploration reference, for the Northwest Queensland. However, it can be expanded throughout Queensland itself, because most exploration areas has very similar setting. The toolkit is divided into two halves. The first part of this, the first 4 chapters, talk about the outcrop or the hard rock domain, expression within that. Basically, it talks about outcropping, sort of mineralization and blind deposits. And it discusses conventional geochemistry. That's what I talked about early in this talk, that, you analyze everything to get the best geochemistry to represent the ore. It also talks about Gaussians and ironstone, how to differentiate it using filters, and it discusses stable and radiogenic isotopes to determine how, to basically model, the pathways as well as the potential of mineralization in the area. The second half of it talks about the covered domains. Basically, this only is practical if the chemical footprints from the ore reaches the sampling zones. And therefore, it emphasized very strongly on the chemical transport mechanism through cover, and talks about faults and fractures that act as conduits and secondary dispersion, especially at unconformable sort of horizons between the country rock and the sediments above. Basically, it's very strong on conventional chemistry, discussing, in comparing the different digestions used in some of this example, looking at biochemistry. We tried soil gas, and it discussed ground water, sort of in exploration as well. This report is available through our QDEX system as report 108260. If you download it from QDEX, you also get the all the data that's used to support this modeling. And so I do encourage you to look at the website and play around with the data. And since it's a published product, I will not go further into this, and I'll sort of move on to the next aspect. The next product that GSQ is trying to release is called the domain map. Basically, this is an isopec map, of sediment covers around the Mount Isa inlier itself. This isopec map is derived from information submitted by company reports through the company reporting system, and therefore we basically translate the lithologic logs into geology. The publication also will have a very prescriptive recommendation of the different sample types to use, for these different domains. And therefore, it is very similar to the toolkit, and it's basically complementing each other. And this product hopefully will be released by by the middle of this year, and it should be another sort of product that will help explorers, especially in the Northwest. The next part of chemistry of this exploration chemistry is, for good successful exploration chemistry, it's really important to understand and use all chemical data to maximize geological understanding. Basically, in most modern analytical sort of packages, it's able to analyze up to 66 elements, and these are the elements that that's the and labs are able to analyze as the first pass package without special techniques. If you look at the different geochemistry, you see that it ranges from alkalic minerals to metalloids to rare earth. However, most of people find it very confusing. What does these different elements represent? Basically, this table indicates the basic control of this chemistry. The ones in beige color basically represents strong lithologic control, whereas the one in cream indicates it could be a crossover between rock-forming minerals or lithologic controls and mineralization, whereas the color in blues are basically all material. So if you've got a high concentration of tungsten, you are sure that you are in a tungsten-rich ore zones already. I've got to get rid of a lot of slides because it's running out of time, but another thing that's important about using chemistry is not to look at single elements, but to look at a group of elements and work using multi-elements analysis that gives you a much better sort of fingerprinting of ore system. Another big question is the trace and rare earth elements. A lot of people, get very confused about this. Basically, they are really powerful, elements. The trace elements generally are all material, whereas rare earth elements will tell you the source characterization as well as for classification, etc. And therefore, I think there are a lot of literature out there that you should sort of, tap in to find the use of rare earth, geochemistry itself. And also, I just put up a sort of, diagram of isotope, geochemistry. It's a really powerful tool to look at fluid mixtures, fluid sources, and that's for stable isotope. And for radiogenic isotopes, the ones that we mentioned in the toolkit, it looked at lead isotope, where it could fingerprint, the ore potential within the Mount Isa region. Next, we look at the archival data that's available in Queensland to help explorer. Basically, what this data does is to de-risk exploration in Queensland. There are basically three major packages. The first package that GSQ has sponsored universities to compile their thesis data. However, because of IP rights, we can't release it through GSQ, and so most university has created their own sites to release their data. So we have data from UQ and data from JCU. The second one is whole rocks, in which we compile GSQ data, Geoscience Australia data and uni data. And again, we can't release it openly, but you can write into us and we can release some of this data to you. The third package, I think Dominic has mentioned this, is the expression geochemistry that consists of drill hole, soil, rock chips, and stream sediments. And this is a really very sort of comprehensive data sets, and there are, that people could use, in the exploration. And then, the last package is various reports where you had value added, or knowledge based reports and data to help explorers. What I've done here is to list some of the sort of projects that's been done by GSQ or collaborate or funded by GSQ that you could download, from QDEX that will help you to de-risk in your exploration within Queensland itself. In terms of exploration geochemistry, this is compiled by TerraSearch and Map2Mine. This is a really good database, I should admit. However, it has a problem that it's really heterogeneous and it's always concentrated in the exposed area of Queensland. There's a lot of gaps in between the data, and gaps means there's more opportunities in Queensland, and there's also a lot of false negative that's below detection limits, which means that there are a lot of area that has been explored, but they are analyzed using very coarse detection limit. And so lots of these areas, all the geochemistry areas are probably areas that you could re-examine, and then this probably has much more potential in these areas itself. Well, the use of this database is basically for pre-planning, and because of the diversity of data, it could be used as a de facto orientation study. And it's a really powerful tool that I really encourage you to sort of look at it before you sort of move on. This is an example of one of the usage. You could use it as a single sort of plot. For example, a soil plot of Mount Isa near the Landsborough Graben, or you could use it as multi elements plots. Like in this case, we use a filter to look at it, where it highlights the high and low of not a single elements but multiple elements. I mentioned before it's a really heterogeneous data sets with many sample types. And this is an example that I've used to process a very heterogeneous sample over the Yarra province to look at the prospectivity in that area. So basically what I did, I turned those data into factors and combined those factors. And this is a plot of the final product where it highlights the high and low. Like, for example, this area for copper in it, is it copper? Yeah, it highlights area of high anomaly around the Mount Morgan area. So this data, it's so diverse, and you could use multiple sort of techniques to find the potential use for that. And the other database that I'm sort of that Dominic has mentioned is a Cape York prospectivity data. And again, this is a knowledge-based data with both knowledge and data incorporated inside it. This first map is the NGSA map for Cape York, for Tungsten itself. And it just shows really broad scale anomaly based on that 550 square kilometers catchment area. But with a more detailed sampling, using this same method on a smaller scale, we could sort of narrow down the tungsten anomaly to very specific points. And this was analyzed, all the sediments were analyzed for 66 elements. And so you had these multi-elements and also multi sort of catchment database that you could use, to actually as a starting point for exploration. This is also, you could see another sort of example is for bismuth, for gold, etc. And being multi-elements, you could combine them as filters or different models to come up with different modeling for that region as well. And you could also look at the concentration of chemistry to work out the chemical or the resource potential of the region. And so that sort of database, what Philip and has done, has high potential as a starting point for explorers in Queensland to cut costs, and to go in and target certain areas for mineral potential. And I think I'll just move on really quickly. It's important for explorers to adopt new technologies. I think I mentioned about the importance of partial extraction, the biochemistry, the high logger, where it used light to determine mineralogy and alteration, and mineralizer, which does continuous portable XRF scans to determine the chemistry of rock itself. And the other things are portable XRF equipment, hydrochemistry, and innovative ways of processing. This is an example of results from the continuous XRF. The grays are logging from the geologists, and these are pics actually from the mineralizer, the continuous XRF scanning itself. And if you look at it, you could see there are a lot of areas that's missed. But by using a continuous scan, you could sort of pick them up. Similar story with Mary Kay. Again, a lot of these equipments are able to do multi-elements, and if you combine multi-elements, you can pick up a lot of missed opportunities in that core itself. This is for Meranon, for Tekil, and for Mary Kay. You could sort of combine them as filters or indices to determine where the ozone is. And I'll sort of touch briefly, this will be a talk, a future talk of using hydrogeochemistry in prospectivity. Basically, the Geological Survey of Queensland has finished a program in the Cloncurry to the Kamilaroi area by taking borehole samples, and both from flowing and static boreholes, and we look at cation, anions, alkalinity, gold and PGE, and stable isotopes. And then it will be a multi-element, 60 elements in a sort of chemistry where we could apply all these indices to understand, the different mineralization style. Also, we take, the depth of the water table, and this information are very useful to vector the water flow, and therefore we could use the anomaly to predict where potential mineralization is. Lastly, I stress the importance of leverage from research and geoscientific organization. I think the Geological Survey of Queensland has been very active, collaborating with a lot of this organization with multiple programs. And there are many programs. These are just some of the examples of programs that we are working towards. And with all these programs, it basically de-risks a lot of exploration in Queensland. To summarize, with this sort of change in the geochemical exploration setting in Queensland, chemistry is really pivotal in any ore discovery, especially undercover. Secondly, geochemical exploration is an integrated science, and it should take advantage of all archival data as well as use new technology and leverage from all the other researchers. And it's also really important to use, adopt techniques that's suitable for the setting, both in outcrop and undercover area. And lastly, when you have a data set, it's important to look at every data and not just selective elements of interest. Thank you.